Okay, guys, 9.2 day 3 should be a little bit shorter today. We're on page 6, of the note packet, number 5, algebraically verifying if two functions are inverses of each other, if they're inverse functions of each other, and if they are, remember, f of g of x has to equal x, and g of f of x has to equal x. So what we will do is we will go into the first one. What is f of g of x? Well, remember that's where I got to plug g of x into f of x. So the way I always did that was I would take my f of x function, and wherever there was an x, I would leave myself some room because I knew that I had to plug in my x to the third over 8 minus 3, and then I had to simplify that. So as I'm moving along here, I got 2. I've got the cubed root. I don't need my root that long because as I'm coming along here, I can see that minus 3 plus 3 goes away and I just have x cubed over 8. Well, that is 2 times, that's really the cubed root of x cubed over the cubed root of 8, which is 2 times the cubed root of x cubed is x, cubed root of 8 is 2, and because that first one's over 1, those reduce, and I get just an x there. So I do know f of g of x equals x. F of g of x, I just proved, was x. That's not enough. I still have to prove that g of f of x is equal to x. And if I can grab my side there, what I do is I'm going to take my g of f of x, means I got to plug f into g, which means I start with my g function, and here's 8 minus 3, and I know I got to plug in for that cubed, so f of x goes in for that x there, which is 2, and that's a cubed root x plus 3. Well, remember your properties of exponents, guys. This 3 cubes both the 2 and that cubed root. Well, 2 to the third power is 8 over 8, and when I take cubed root of x plus 3 to the third power, I just get x plus 3, and then that's minus 3. I can see my x's reduce, and I get x plus 3 minus 3. My 3's go away, so I can see g of f of x also only equals x. So yes, they are, yes, inverse functions. Why don't you pause it here quick and give number 6 a try. Okay, well, we'll see how you did here. Remember, I'm finding f of g of x first, so what I did was I plugged g of x in where x is in my f of x function, and now I'm just going to simplify that little bugger, and I get 3 times. Well, the first thing I do is that goes away, and I have 3x over 3, and that's cubed. Well, that cube kills that cubed root, so I really have 3 over 1 times x over 3. Those 3's reduce, so I find out f of g of x actually equals x. Okay, what about g of f of x? What does that equal? Well, that's where I want to put f into g. So I'll start with my g here, and I got a big old cubed root. And it's a 3 on the bottom, and minus 1. And I'm going to plug in my f of x function in there, which is 3 times x plus 1 cubed. It's really important you follow the order of operations on these as well, because you can't just start hacking and slashing. Things need to go out at the appropriate time. First thing underneath here, those 3's reduce, and I get the cubed root of x plus 1 cubed minus 1. Well, then that cube gets rid of that cubed root there, so I have x plus 1, technically minus 1, and I can see plus 1 minus 1, and I find out g of f of x also equals x. So yes, inverse functions. And it just warms up. It's reinforcing what you did yesterday algebraically for inverse functions. Okay, this one right here is just some happy little facts. If you want to pause and read this, talking about surface acceleration in some word problems here. To be honest with you, a lot of this stuff isn't overly needed for the next problem. They're just really a few fun facts here. I can pause that and finish reading it. And I'm just going to come down here. The 10,000 year clock, we're looking at an application. Okay, the time it takes for one complete swing of a pendulum depends on the length of the pendulum and the acceleration due to gravity. Okay, this is true. It's actually a fun little lab we do in calculus. The formula for the time it takes a pendulum to complete one swing is t, the time it takes, equals 2 pi times the square root of the length of the pendulum divided by this g. That g is not a constant, or is not a variable. That's a constant. Okay, t is in terms of time, L is the length of the pendulum in meters, and g is acceleration due to gravity, for those in physics, at 9.8 meters per second squared. So what I'm going to do is I'm just going to say, well, if I write the function, the length of the pendulum, or time in terms of the length of the pendulum, time depends on the length of the pendulum, equals 2 pi times the square root of L over 9.8, because that's what g is. That's the acceleration due to gravity. Okay. Now they're just going to say, hey, they want us to graph this function. Not too bad. If I really look at it, okay, it's nothing more than an ugly square root, and the only thing I cannot have happen underneath that is I can't have it be negative, so my domain has to be all x's greater than or equal to 0. And I can't use x's because this is the length. I got to say it's all l's greater than or equal to 0. In my range, because it's an invisible plus sign, if it were the negative side, the range is going to be time here is always going to be greater than 0. Well, that makes sense because time can never be negative. If I put a 0 in for L, okay, this is technically my t-intercept and my L-intercept here, length and time. Okay, so if I put 0 in for L, I get 0 out, and if that's that intercept, it's obviously going to be that one. I'm kind of starting out here at 0, 0, and if I had to graph that, well, to be honest, it's a pretty ugly graph with 2 pi, so all I did was I didn't make an XY chart. I made a LT chart, okay, because, come on here, I put in an L to get out a T. That's why I'm saying it's an LT chart, okay? L is my independent variable, and T depends on what I put in for L. So if I put in a 1, I did these calculations already. Well, all I really did was I put a 1 in there for L, and I took 2 pi times the square root of 1 divided by the square root of 1 divided by 9.8, and what it gave me was roughly 2.007. So I'm going to come over, and it's just a hint over 2. And then if I put a 2 in there, I came up with 2.838. So if I came over 2, I'm up to a little bit under 3. And then if I put 3 in there, what I found is I got 3.476. So when I put in 3, I got out about 3.5-ish. And what we see is it's a square root. Don't really like how I got that one there. So I'm going to, whoa, leave that little bugger there. And it's going to kind of come out like that. There's the graph. Just making a couple points in there. How long does it take for one complete swing when the length of the pendulum is a half a meter? Well, that's asking what t of 0.5 is. Well, what that is that's 2 pi times the square root of 0.5 divided by 9.8. You let your fingers do the walking in the calculator, that's about 1.42 seconds. Okay? And a typical grandfather clock pendulum completes one swing in 2 seconds. Use the graph to determine the approximate length of the pendulum in a typical grandfather clock. Well, completes one swing in 2 seconds, so that's time. So what I'm going to do is I'm going to come to my time axis, and I'm going to come across here where 2 is, and I'm going to cross-reference that down. Oh, it looks like that's roughly about 1 meter. Okay? And that's about how long the pendulum is on a grandfather clock. It's just an application problem of doing what we did in there. Now, rewriting the function t of L as L of t, where the length of the pendulum is a function of time for a period. Well, right away, right now, we're t, time, equals 2 pi times the square root of L over 9.8. Notice this didn't ask me to find the inverse function. This just said right now, this is time in terms of length. Now they just want me to rewrite it as length in terms of time, and all that's asking me to do is to solve this equation for L, okay? So what I'm going to do is I'm going to divide by 2 pi first, and I'm going to have t over 2 pi equals the square root of L over 9.8. Next thing I need to do is I need to square both sides. And when I square both sides, I'm going to get L over 9.8 equals, well, time squared is t squared over 2 squared is 4, pi squared is just pi squared. And then I still have to multiply by 9.8 on both sides, 9.8, and then that gets rid of them there. So the length now is 9.8 t squared over 4 pi squared, and that's basically what they just had us do. This equation that we just have right here, this is the length in terms of time. The length depends on time, and it's 9.8 t squared over 4 pi squared. Whoop. And any questions on that? Remember, we're, I think, 9 to 10:30. Oh, this stupid board drives me nuts. 4 pi squared. Now I can circle the length in terms of time. Okay? And hope things are going well. Please feel free, if you can't make those office hours, anybody, please feel free to shoot me an email and we can set something up. Have a good night.